Hello everyone, so this is going to be Unit 3 Dynamics, Part 2. So last time we ended off here, and we're just going to go to the next question. So a ball of mass m is thrown vertically into the air. When the ball has speed v, the air resistance acting on the ball is f. What is the magnitude of the acceleration of the ball when its speed is v as it rises and as it falls? Okay, so we have two different parts, and then we just have to match each one. So first we're going to do as it rises, and then afterwards we'll do as it falls. So as it rises, and as it falls. So when it rises, our ball, right? Let's say this is our ball. We throw it with a certain velocity upwards, and this is like completely unrelated because they're not asking for it. You're asking for the actual acceleration, which is the resultant. So since it's going up, we know that our air resistance drag force is also going to be down. And then another downward force is for G. So we can convert this. This is drag force, right? F equals ma. We can just say like F drag is equal to ma. And then it becomes F drag over m equals a. And then gravity, this is actually mg. If we divide m, we have regular g. So in this case, it's going to be g plus f over m. And then we can eliminate 2. And then as it falls, so we have our ball here. This isn't actually a force, I shouldn't have wrote it, but it's just like the direction the ball is going. But now, this is our second free body diagram. So we have air resistance, which is going to be F drag. It's because it's falling down, right? Then since it's falling down, the drag force should be going up. And then we have our gravity mg. So then it's just going to be, this becomes F drag over m equals a, and this becomes mg over m is equal to g. So then since they're going in opposite direction, they're obviously going to be subtracted. So g is going down, so it's like g technically is negative g, but it's going to be g minus f over m, so it's just going to be c. It's not d because they're actually going in opposite direction, so you subtract it. I'm not entirely sure how AICE actually does like directional forces. Are you saying like up and down? But since they're going opposite directions, you have to subtract them, and then if they're going the same, there you add them. So that's the general rule you should follow. But yeah. In the absence of air resistance, a ball is thrown horizontally from a tower with velocity v will land after time t seconds. If, however, air resistance is taken into account, which statement is correct? So horizontally v, so then the distance would be vt, assuming that there's no air resistance. But if there is air resistance, then if we draw a short free body diagram, so we have a ball, right? It's thrown here, but then we have drag force. So F drag. This is actually wrong because there's no force. There's no resultant force. I don't think. Yep. So then, since the only resultant force is going to be the drag, after a while, our v is actually going to slow down. So it's decelerating basically. And if we use the fact that this will decelerate, we can say that C and D should not be the correct answer because they say that, oh, our velocity didn't change at all, which is not true. Because we will decelerate after some time t. So we are left with two answer choices. The balls land with horizontal velocity less than v after more than t seconds. And then we have the ball lands with a horizontal velocity less than v after t seconds. So they both seem somewhat viable, but it seems like A would be the more correct answer because they don't really state that t is non-zero. But we can assume that it's non-negative since it's time. So, for example, if we take our ball, right, let's say t is equal to 0. After t seconds, our ball doesn't move at all, but it's still technically moving at a velocity of v, which contradicts this less than v stuff. But if it's strictly greater than 0, then after a certain while, it can be like 0.001 seconds, we will still decelerate by like a small amount. I hope that makes sense. Each diagram illustrates a pair of forces of equal magnitude. Which diagram gives an example of a pair of forces that is described by the Newton's third law of motion? Okay, so Newton's third law of motion is just saying equal in opposite direction, opposite reaction, sorry. So equal just means same magnitude, and direction means direction. They should be going in opposite directions. So we can look at it so far. Seems like all answer choices seem to have equal direction. I should also mention that equal also means same type of force. So we look at A, we have driving force and total resistive forces. It's not going to be this one because if you think about it, there isn't like the same type of force. So this driving force is actually thrust, and then this drag force is friction plus drag, which is basically friction but with air. But like essentially these are two different things because thrust is generated by the engine and friction is based on the air. B, it seems that we have gravitational attraction and gravitational attraction, so they seem to be somewhat the same type and the same magnitude, and they go in opposite directions. So one goes towards moon, one goes towards earth. So it's most likely going to be B. Let's look at the other choices. So C, support force and weight. So these are not the same forces, and the same thing goes for D. So basically we can just select B. So for this problem, we have to make sure that the two forces that we look at are in opposite directions. In this case, it's provided that they're in opposite directions. But the second thing we have to check is that they're actually the same type of force with the same amount of magnitude. Okay, what describes the mass of an object? Okay, I'm pretty sure this is okay, so immediately the first thing you should think of is space, even though that's not the right definition, but that's the first thing you should think of. And quickly glance over the answer choices and see that the force experiences due to gravity, no. Momentum, probably not. Resistance of an object, no. And then weight, no. Okay, so we quickly glance over and see that our definition is not about space taking up. And if you think about it again, then we think about Newton's second law, I believe. So it just describes how the resultant force will every object has inertia basically. And this inertia is actually based on the mass of the object because, for example, right, if you try to push like one of your friends, right, they'll obviously move, but then if you try push like a giant boulder, the boulder is like much more massive than your friend. That's because it has so much more mass, and because of that, we can just say that it's like inertia or resistance to forces basically. The force, okay, so then we can look at our answer choices and see that A obviously does not make sense. The momentum is somewhat related to the mass of an object, but it's not talking about like before collision. Not everything is a collision. The resistance of the object, it changes in motion. So this is actually what I was just saying. Same idea, different words. That's how you do the SAT, by the way. The weight of an object as measured by balance. So weight is not the same thing as mass. Because weight is based on actual gravity. And weight is actually a vector. So which statement follows directly from Newton's second law? A body remains at constant velocity unless acted upon a resultant force. A satellite in circular motion about Earth has a constant velocity of water drop. Okay, so generally you should read the question and then look at the answer choices to get an idea of what they're talking about. If you don't know what Newton's first law, you should try and remember it. But I'm pretty sure it's like something how like something will stay in motion unless an object acts upon it, and an object at rest stays at rest basically, because it's like, oh my god, object is at rest and stays at rest because nothing is moving it, but like if you kick it, for example, then obviously it's going to move forward. So unless some outside force affects it, then it's not going to move. So then we can look at each of these kind of. So a body remains at constant velocity until acted upon a resultant force. Okay, so that's pretty much what I said. A satellite in circular motion about the Earth has a constant velocity. We might not get to this, but I'm pretty sure Earth does have a centripetal force. Centripetal and centrifugal, I'm pretty sure we don't cover in AICE, but something worth knowing that exists. So an object is actually moving like this, and then Earth is actually pulling it this way. So there is actually a force, I'm pretty sure. So it's not necessarily constant. And I don't know if this reasoning is correct, but I believe that's how it is. A water drop leaving a spinning umbrella travels at constant speed. Okay, so this is incorrect because we don't leave, stuff doesn't fall down on Earth at a constant velocity. As this is because it's due to gravity, and gravity will always accelerate stuff down. And the force acting on an object is equal to its change in momentum. No, I don't think so. Because momentum is actually an S. So we can just say it's not D, because when you're talking about Newton's first few laws, you want to disregard momentum at all. Because they don't even talk about momentum, they talk about forces and how they affect an object. Momentum is actually unit 6, which we'll get to, I'm pretty sure. Alright, so a person of mass 60 kg stands on an accurate bathroom scale, is placed on the floor of an elevator, lift, British people, am I right? Just kidding, that's banter. Which operates in a tall building. At a certain instant, the bathroom scales read 58 kg. Which row could the person's direction of movement and type of motion? So let's draw a little elevator. So we have our bathroom scale and then our person. Let's just assume he's actually on the bathroom scale. So yeah. So you're actually 60 kg. And then at a certain instance, the bathroom scales read 54. So let's say like you're standing in motion, standing like idle. Then your constant force will be 60 down here. So then if you're standing, right, it's gonna read 60. Assuming that it's accurate, which it is. And then now I have to figure out what makes and what circumstance changes it such that our little person here, how do we make it so that our weight is now 50 kg? Well, we can see that this is 60 and this is 58, right? And then we have a direction of motion, so that means we introduce a new vector. And since we're originally 60 kg, this 58 is actually the sum. Oh, what the hell? So this is force. That's the sum of the forces, the resultant forces. Oh, it hit 12 a.m. That's probably why it came up. So that means that we have a force that's going up basically. And it's about 2 kg-ish. So since we know that it's actually going up, I should write that this is not like 50 kg, this is 60 kg. We just assume that the sum of forces is about 58 kg. So then if we go up 2 kg, this becomes like 60 minus 2 kg, which becomes 58 kg. So then it's not going to be A or B since we know that it's going up, and we have to figure out if it's going up constant speed or slowing down. Okay, so if it's going at constant speed, that just means that our acceleration is 0. And then if we use our definition of F equals ma, our force is going up, so our force is greater than 0, and our mass is a constant basically. And if we say that we're going at constant speed, that means our acceleration is 0. And this does not make sense at all because our force is greater than 0, but we have a 0 value. We have it equal to a 0 value. So there's no way it could actually be C. Mathematically, at least, theoretically. And then we have D. That's the only variable answer that's slowing down, because that means that our acceleration is non-zero. Also, it says in the problem that at a certain instance, that just means that at some point, so it could be like going really fast and like slowing down, whatever. But yeah, so this problem is basically using the idea of resultant forces. So initially our resultant force is 60 kg standing, and then once it's moving, our resultant force is now 58. And then we have to use mathematical ideas like the motion here. The constant speed means that acceleration is equal to 0, which is not what we want. Okay, a rocket is fired into space. Newton's third law of motion describes how forces act in pairs. One of the forces of a pair is the weight of the rocket. What is the other force of this pair? So I don't care about the shape, but this is our rocket, guys. It's a nice rectangular box. One of the forces of a pair is the weight of the rocket. So they give us one of the pair, so we have to find out the other pair. So it's gonna be mg. So weight is based on Earth. So then, that was my cat, by the way. So then, we have an opposite force that's going the same way here from Earth. So yeah, I don't think I explained it, but this is also equal and opposite reaction. Equal in magnitude, but opposite in direction. So it goes down, but then Earth goes up. And then we can see that the only answer choice here that mentions Earth is D. So that's going to be the correct answer. Yeah, so also I should mention that the weight of the rocket is the force of Earth on rocket, and thus the opposite reaction would be on the two different objects, force of rocket on Earth, which is basically what he's saying. Which statement must be true for an object in a gravitational field? Okay. I guess we go by one. So if an object has mass and a gravitational field, then the field causes it to accelerate. So if I use Earth as an example of a gravitational field, oh my god, we can say that Earth is our gravitational field, I guess. And then if an object has mass, then the field causes it to accelerate. So that means that if we have an object that exists that is not something different, that is just like something that is existent. Sorry, it's getting late. If something exists, then it's saying that this thing will accelerate. But if you have a ball and then you drop it, that's obviously going to accelerate. But what if the ball's on the ground? Will it still accelerate? Maybe infinitely, but theoretically no. Because the ball's on the ground, it's not moving, so it's not accelerating, and it's not moving at a constant speed. Because the resultant force is 0. If the object has mass, then the field causes it to have weight. So like if you hold a ball, you can feel it actually going down, and that's because of gravity. So if you have a hand, that's how you draw a hand, and you're holding your ball, but it's going down mg, you can feel it actually doing it, actually like putting weight on your thing. So maybe if an object has a weight, then the field causes it to accelerate. So weight implies that it already has acceleration. So I'm unsure how this makes sense. So if it already has weight, then it should already be accelerating, basically. And I'm guessing this like statement is like implying that we start from 0 acceleration, which is not true at all. And then D, if the object has weight, then the field causes it to have mass. what did I just read? Okay, this doesn't make sense at all because weight is actually dependent on mass. So this is obviously not it. I hope that is as clear as I made it. I hope it's clear that this is obviously wrong because weight is actually ma because that's what it is. That's what Newton's second law states, and our mass actually it should be the other way around because if our field has mass, then it should have weight. So and that's B. So that's kind of funny. Okay, so this is the last problem. The diagram shows two parachutists X and Y moving vertically downwards. The total mass of parachutist Y and his parachute is twice the total mass of parachutist X and his parachute. At this moment, the air resistance on parachute Y is twice the air resistance on parachute X. Now that parachute has reached its constant terminal velocity, which statement describes the acceleration of Y compared to the acceleration of X. Okay, so we can actually draw the free body diagram. So X here has an upward force, which is going to be air resistance, F drag. And then down here, gravity, basically. I know like the vector looks kind of like F drag looks larger, but we can assume that this is actually larger than that one. For clarity, we can call this mxg because the mass of parachute is x times gravity. And then in this case, we have the parachute y, which is myg, and then up here, which is actually in this case 2f drag, because it says in the statement that the air resistance is twice the air resistance on x. The air resistance on y is twice the air resistance on x, so it's 2 times drag. So we can find the resultant forces for both of these things. So we have f of x, which is the x parachutist, so it's going to be like mxg minus f drag. And then for parachutist y, it's going to be myg minus 2f drag. And then we can substitute this my because we know that my is equal to 2 times mx. Based on the first sentence of this paragraph, the total mass of y is twice the total mass of x. And this becomes and we can actually calculate the acceleration based off of this. So we can use the acceleration. So you know that F equals ma, right? So then, since we know that this is our resultant force, we only need to divide by our total mass to get A. So then we can take like 2mxg minus 2f drag over 2my. No, not 2my, sorry. It's just going to be my, which is essentially going to be 2mx if we substitute it in. So this is mxg minus f drag over mx. And then I have to calculate the acceleration of the x parachute. So we can still use the fact that we divide by the mass. So since we have our resultant force, mx minus g minus f drag divided by our mass, which is going to be mx. And this becomes mx g minus f drag mx. And then we can see that this is actually equal to our f of y calculation. So that means that both of these parachutists have the same amount of acceleration, which is going to be b.